Powered Parachute Handbook 4.1 Powerplants. Let's delve into the engine realm of powered parachutes, the true powerhouse. This section covers everything from exhaust and ignition to fuel, lubrication, cooling, propellers, gearboxes, induction, charging, and fuel systems. We'll explore the intricacies of reciprocating engines, examining both the 2-stroke and 4-stroke varieties. The engine and propeller combo, often called the powerplant, is like the dynamic duo, not just pushing the powered parachute through the air but also fueling up the electrical system that keeps the whole operation humming. Maintaining this engine is key, and you want to stick to the recommendations from both the engine and airframe experts. The pilot's operating handbook and the manufacturer's maintenance guides hold the golden rules. Don't forget to keep a logbook detailing all the inspections and maintenance. It's like the engine's own little journal. Most powered parachutes roll with reciprocating engines. We can categorize them in two ways: by the number of piston strokes, 2-stroke or 4-stroke, and how they keep their cool liquid or air-cooled. 2-stroke engines are pretty popular because they're simpler, lighter, and more budget-friendly. Plus, they pack a punch in the power-to-weight ratio department. 2-stroke engines have a cool history, evolving from snowmobile and watercraft engines. What makes them stand out is that we mix oil right into the fuel for lubrication. No separate oil systems like those fancy 4-stroke engines. Now, let's dive into the mechanics. Picture it like a sequence in two parts: the intake and compression stroke, followed by the power and exhaust stroke. We've got different valve systems doing their thing: reed valves, rotary valves, and good old piston porting. Piston porting means the fuel gets in and out based on where the piston is in the cylinder. The 2-stroke process starts with the piston going up, creating a vacuum that pulls in the fuel or air or oil mix from the carburetor. On the way down, it gets compressed, and when the piston's at the bottom, the mix shoots up into the main cylinder, pushing out the exhaust. This engine talk is like getting backstage access to the symphony of powered parachutes. It's all about keeping things in tune, following the mechanics, and making sure the engines are in top shape. So, before you hop into an unfamiliar powered parachute, flip through that logbook, and ensure the engine is ready for action. Now, let's break down what happens in the cylinder during the compression and power strokes. As the piston moves up, it compresses the fuel mixture in the combustion chamber while the crankcase vacuum intake process continues simultaneously. This dual action is why 4 processes can happen in just 2 strokes. Moving down into the power stroke, the spark plug ignites the fuel mixture, propelling the piston down in a burst of power. As the piston reaches the exhaust port, exhaust gases start to exit, and the transfer port opens, allowing the fresh air or fuel or oil mix to push the exhaust out. As the piston reverses direction from the downstroke to the upstroke, this completes the process. This visual illustrates the cycles in a 4-stroke engine. These are pretty common in various aircraft, and they're becoming more popular in powered parachutes too. They offer reliability, fuel economy, longer engine life, and higher horsepower ranges. But, of course, there's a trade-off. They come with a higher acquisition cost, lower power-to-weight ratios, and a bit more weight overall due to extra components like camshafts, valves, and a complex head housing the valve train. These are crucial for venting burned combustion gases, reducing engine noise, and for 2-stroke engines helping keep the fresh fuel-air mixture in check. Exhaust systems have piping attached to the cylinders and a muffler. Some even sport an exhaust gas temperature probe, transmitting readings to an instrument in front of the pilot. This helps monitor the exhaust gas temperature, offering insights into power and fuel-air mixture specifications. In the realm of 2-stroke engines, tuned exhaust systems play a vital role. These systems increase fuel economy and power, acting like an exhaust valve. They're designed to produce a back pressure wave for scavenging, helping clear out spent gases and pull in fresh fuel-air charges. Pulse charging, another important function, is achieved through the returning pressure wave pushing the fresh fuel-air charge back into the exhaust port before the cylinder closes it off. Tuned exhaust systems are often tuned to specific RPM ranges. While motorcycles can optimize this through transmissions, aircraft lack this luxury, requiring a broad RPM range design. Matching the specific design of the 2-stroke exhaust system to the engine is crucial for proper operation, achieving rated power, reducing noise, and directing exhaust appropriately. Adding exhaust silencers can mitigate noise but comes with additional weight, cost, and a slight power reduction. When it comes to 4-stroke engine exhaust systems, they're not as finicky as their 2-stroke counterparts. Thanks to exhaust valves, they don't require the precision of a pulse-tuned exhaust system. Nonetheless, directing the exhaust appropriately and reducing noise remain important considerations. Sticking to the manufacturer's recommended configurations is a must for special light sport aircraft or SLSA and is recommended for experimental light sport aircraft or ELSA. Now, let's talk about the unique ritual of warming up two-stroke engines. These engines demand a bit of TLC before they hit the skies because different metals in the engine expand at different rates when heated. Imagine heating up steel and aluminum. The aluminum parts tend to expand faster than their steel counterparts. This can cause trouble in two main areas of many two-stroke engines, starting with the cylinders. Cylinders have steel walls that expand slowly compared to aluminum pistons that expand rapidly. If you rev up the engine too quickly during takeoff before it warms up, the piston can quickly expand and seize in the cylinder, bringing the engine to an abrupt halt. The second area of concern is lower in the engine around the crankshaft, where things might get a bit too loose with heat. The crankcase has steel bearings set into the aluminum, and they need to expand together to avoid slipping. A proper warm-up procedure ensures that all parts expand evenly. Many two-stroke engines are best warmed up by running them at a set RPM for a specific duration. While you should always follow the instructions in your PO, a general rule of thumb is to start the engine at idle RPM, get it operating smoothly, and then warm it up at 3000 RPM for about 5 minutes. Even after warming up and taking flight, there's a risk of cooling down the engine too much during extended idle periods. A sudden power application with a cooled down engine can lead to a seizure, just as if the engine hadn't been warmed up initially. In water-cooled engines, a long descent at idle can cool the coolant until the thermostat closes, maintaining a set temperature. Applying full throttle without gradually adding power can result in a piston seizure. As for four-stroke engines, they also require a warm-up. These engines boast a pressurized oil system that provides uniform temperatures to all components. You can hit takeoff power as soon as water, cylinder head temperature or CHT, oil temperatures, and oil pressure align with the manufacturer's recommended tolerances for takeoff power applications.